Okay, so a problem for matrix algebra is this: find the real eigenvalues of the given matrix and their associated eigenvectors. Well, for that, we have to make a translation first. What are we trying to find? So first, what does this mean? Recall that lambda is an eigenvalue and v, different from 0, vector, is an of lambda, of course. If the following equation is actually holds, if a times v is equal to lambda times v. In other words, the action of a on v is just a scalar multiplication on v. Well, but in order to find them, this is what I'm going to do. I'm going to take this equation that I have here and then rewrite it in different terms. So I have a v minus lambda v is equal to the 0 vector. But then from here, I'm going to introduce the identity matrix. Well, what is the identity matrix? The identity matrix, in the case of the 2 by 2, is nothing else but this matrix: 1, 0, 0, 1. So if I multiply this against a two-dimensional vector, I'll just get that two-dimensional vector. Well, let's see. From here, I get the following equivalent equation: a v minus lambda times the identity times v is equal to the 0 vector. In other words, from here I may factor v. This is just matrix multiplication. So I have a minus lambda times the identity times v is equal to 0. So look at the conditions that we have here. We're requiring that a is different from 0. And look, this is just a matrix. So this is indicating that the nullity, or I'm sorry, not the nullity, but the null space associated with a minus lambda I is a non-trivial subspace. In other words, for this to be non-trivial, that means that the matrix a minus lambda I is singular or non-regular, as you may find it in some textbooks. But for this to be singular, that is equivalent as to indicate that the determinant of this matrix is equal to 0. Zero, the number itself. So what we have done, what we have here is that we turn a problem of matrix algebra into a problem of just college algebra. Look, what we have here is just an expression, a polynomial expression in lambda, as we're going to develop. Because what this says is that the determinant of, well, let's copy it from here. We have 2 minus lambda, -3, and then 2 minus 5 minus lambda. So the determinant is 0. What is the determinant of 2 by 2? Well, this is a classical problem. It's just the difference of the product of the diagonals. So in this case, we can expand it here, and we have 2 minus lambda times -5 minus lambda minus 2 times -3 is equal to 0. So I'll continue with this, and this says, multiplying here, I get -10 minus 2 lambda plus 5 lambda plus lambda squared plus 6 is equal to 0. Let's convert this. What we have here is nothing else but lambda squared, combining these ones, plus three lambda minus 4 equal to 0. I'll break it up. So now we have, look at this. this is just a quadratic expression in lambda, so it may be prone to factorization. So I'm looking for two numbers that when multiplied will give you -4, and when added will give you 3. Well, I think that's simple. So this is just lambda -1 times lambda plus 4. But now this is easy because we're dealing with real numbers. This happens if and only if lambda is equal to 1 or lambda is equal to -4, right? That means that the only eigenvalues that are possible are these two. So now, how do we find the eigenvectors? What I'm going to do is choose one of this, and then the process is going to be repeated for the other one. Look, we go back and explore the conditions. It says that the null space associated with this matrix should be different from the trivial subspace. So, recall. We must have that the null space of A minus -4 times the identity is non-trivial. But then this one, what does this mean? Well, let's interpret. The null space of A minus, well, actually plus 4 times the identity is equal to the null space of what matrix? Well, that should be 6 minus 3 to -5 plus 4, so -1. But then, what does this mean? Well, let's see. For any particular vector to be here, it has to satisfy a certain condition. And what is that condition? So, recall that a vector x1, x2 on the plane is a member of the null space of this matrix. Well, if and only if, when you multiply it, 6, -3, 2, -1 times x1, x2, that results in the 0 vector. But then, well, this is nothing else but a system of equations, actually a homogeneous system of equations, which now might be represented with the following augmented matrix. 6, -3, 2, -1, 0, 0. Of course, we start with the reduction process. What I'm going to do is multiply the first row by by 1/3. So I'll get 1/3 of row number 1, and that results in 2, -1, 2, -1, 0, 0. And then look, these are identical. So what I'm going to do is subtract. So to row number 2, I'm going to subtract row number 1. The resulting equivalent matrix is 2, -1, 0, 0, 0, 0 on the augmented section. So what we're going to do is recover that system, and that says the following. 2x1 minus x2 is equal to 0. Look, this row gives you no additional information. This only tells you that 0 is equal to 0. Thanks for telling me something I already know. So for this one, we'll get now this equivalent expression. X2 is equal to 2x1. So in other words, a vector is a member of this collection if and only if this is satisfied. In other words, all such vectors have the form x1, x2, but with this equation, right? With this additional condition, we have that x2 is just 2x1 and x1 is just x1. But from here, look, I can extract the following. This is just 1, 2 times x1. So every single member of this collection can be written as just a scalar multiple of this. That means that the eigenvectors associated with this eigenvalue, well, are nothing else but the non-zero scalar multiples of this. So we're done. And with this, we finish.